All righty. Before we get started, just want to say thank you everyone to coming, and we're really excited to have Abhishek Nagaraj presenting his work today, and then Ryan Hill will be discussing. A couple of notes on the format. We'll have a 40-minute presentation. If you have questions throughout, please put them in the chat, and we'll try to pause throughout for Abhishek to answer them. He might also have some co-authors who might answer the chat as well. Then Ryan will give a 15-minute or so discussion, and then we'll have some more Q&A at the end. Please join us for our next WEFI in 2 weeks on Halloween with Julia Fonseca. And then, also, we would love if you could put your cameras on just so that we're not looking into, or at least specifically Abhishek is not going to be looking into a blank void. That would be great. But with that, let's give it, I just got to the 2 minutes after, so let's go ahead and get started. Abhishek, take it away.
Thank you so much to the organizers for having us. Really excited to be a part of this amazing community and share some of this research. The title of the talk is The Streetlight Effect in Data-Driven Exploration. And this work is really the brilliance of my co-authors, Matteo Tranchero, who's at Berkeley, and Gustavo, who's also here. And Johannes Hoelzemann will be, I think, joining us in a few minutes, so they can also help answer questions if you have them in the chat. So with that introduction, kind of let me jump in. The starting point for our work is the recognition that a lot of innovation and entrepreneurship is about exploration under uncertainty. So think about when pharmaceutical firms are deciding which different drug targets to fund, or a venture capital fund deciding between different potential startup leads that they have, or even in more classical cases, such as mining and exploration, where a firm is trying to decide between multiple different locations where to invest their exploration dollars. In each of these settings, these firms don't have a great sense of which of their potential leads or targets are really the best ones to invest their investment money. And so a lot of the process of innovation and entrepreneurship is actually about resolving that uncertainty. Now, this mechanism and this way to kind of look at innovation and entrepreneurship probably captures what has been going on in this field for many decades, if not centuries. But there's been a recent trend that has really started to shape how this process unfolds. In particular, the data revolution is reshaping how firms make these kinds of high-stakes decisions. Now, this could be through literal data, so some new data sets and maps that give us a sense of whether I should look for gold in location A or B, or data and analytics technology and machine learning that is helping a venture capital firm tell the difference between two startups that otherwise look exactly the same. The way that we kind of think about these tools is that they shape exploration by providing signals on the value of some of these options over others in high-stakes decision-making. So if I see these two options that otherwise look quite similar, a data analytics tool might tell me that, look, option one is going to be more promising, is going to have a more positive signal as compared to option two, and that can shape or change my cost-benefit calculations as I decide in terms of my investment decision. Now, some past work has started to look at the role of data in shaping this kind of exploration. So in my own dissertation, I looked at how satellite imaging and satellite mapping shapes exploration in the mining industry. And here we showed that the arrival of randomly assigned data in some parts of the world as compared to others double the likelihood of new discoveries in this industry, and that these discoveries are much more likely to come from new entrants or startups in the space as compared to incumbents. There's a bunch of other similar work as well that's starting to kind of make this association. So Matteo, who's my co-author on this project, his dissertation looks at how genome-wide association mapping, GWASs as they're called, can provide a similar mechanism in terms of shaping drug discovery. And increasingly, there's the discussion in venture capital. There's some venture capital firms set up explicitly with this hypothesis that a more data-driven decision-making might actually make kind of what they're doing more efficient. let me also point out, like, my Discussant's work. Ryan has some amazing work on protein maps, and kind of like, and I think there's a bunch of recognition in that field as well, that those kinds of databases are also reshaping innovation in terms of how it happens. So there's a bunch of both anecdotal examples as well as some systematic evidence that this kind of change is really helpful for search and exploration. Now, despite these case studies, recently, Brynjolfsson and co-authors report from some survey data conducted across a variety of manufacturing firms, but they show that a more data-driven decision-making has yet to translate into productivity gains. So when you look at it from a different perspective, this kind of change isn't really translating in any kind of major improvements in the ways in which firms innovate and discover new technologies. So it seems like data-driven decision-making might not be a panacea for innovation and entrepreneurship. And that really sets the stage for the key question that we ask in this paper is, are there some conditions under which such kind of decision-making might actually hamper rather than help individual and social performance in terms of making the most optimal decision or discovering a breakthrough in a given area. We'll develop, this is a theoretical and experimental paper, and our theory will be based on this anecdote of this cartoon of the streetlight effect that a few of you might have heard of. The streetlight effect is basically comes to an old anecdote or almost an old joke where a drunk man is looking for his keys, and a policeman comes up to him and asks, what are you looking for? He said, I'm looking for my keys. The policeman says, is this where you lost them? And he says, no, I lost them kind of on the other side of the road, but I'm looking here because this is where the light is. Right? So the streetlight effect highlights this tendency to focus on particular questions, cases, and variables for reasons of data availability rather than a broader relevance or policy importance. Right? And so what we're going to try to do is a model or provide a formal model of the streetlight effect and try to understand how it might shape exploration and decision-making under uncertainty. So in particular, our model will be based upon a multi-armed bandit. I'll talk about it in a second, but just to give you a preview, where a variety of different firms will be choosing amongst a variety of different risky options, exactly in the way that we saw before. Data, in this case, will be modeled as signals, or in this case, explicit clarifying of uncertainty, where firms will learn about the value of one option over everyone else, right? So it's going to clarify uncertainty about one option of the menu of options that they have, and they'll learn about a low value option, a high value option, or a medium value option. So the data will shine a light on different types of projects that firms don't know much about ex ante. And our key result will be the value of the streetlight, the value of data will matter based on what kind of project is illuminated. When data shines a light on low and high value options, it'll increase private performance and the likelihood of discovering the optimal option. So this is those case studies that we saw before, right? So data clarifies uncertainty, and that's going to be really good for innovation exploration. However, we're going to develop this relatively novel hypothesis that data on the medium option, and then I'm going to clarify what medium means in this context, will actually end up decreasing private performance and the likelihood of discovering the optimal option or the breakthrough amongst all of the different options on the table. So a bunch of my talk will be about clarifying what this medium option is and how the amount of light we shine on different types of projects can shape exploration. They will then test this theory in an online lab experiment where we'll have individuals engage in this kind of high stakes decision making, and then we'll shine a light on different kinds of projects. And we'll validate our theory by looking at how individual payoffs, as well as a group likelihood of discovering the breakthrough, is shaped by clarifying different types of uncertainty. And we'll find that when we provide medium data, it reduces private payoffs by 11%, even compared to the option when no data is provided at all. Right? So you might have a model where information can only help, and our setting is going to show you that that actually doesn't happen in the setting. In fact, the likelihood of discovering the breakthrough option goes down by a whopping 71%. So we see the experiment as a validation of the theory. There don't seem to be big discrepancies between kind of our theoretical predictions and the role of the experiment. This work contributes to a lot of different streams of literature and broadly speaks to work on the exploration exploitation trade-off that a bunch has been written about both in economics and in finance, including my co-authors, Gustavo's work on this topic. A bunch of management and innovation literature provides these case studies that I talked about before on the role of data and early stage signals in shaping exploration. In particular, Mike and Ramana and a bunch of others have done great work on things like cloud computing and how that shapes the decision-making and funding decisions of startups. And a lot of this work has these models where early stage signals greatly clarify decision-making and improve performance. And so our work kind of speaks to that by highlighting cases where that might not entirely be the case. There's work in the IT literature on the role of data that I alluded to before. As well as there's an economics literature on strategic experimentation and social learning. A lot of that is experimental and in the lab. And our work really speaks to that literature as well, because it really hasn't looked at the role of information or data in shaping exploration processes. So let me pause here for a second and make sure everyone's following before I kind of keep going. Good? Awesome. Thank you. So the setup for the rest of the talk is as follows. So spend some time giving you an intuition of the theory. We won't have time to walk through all the proofs and the propositions, but I think we'll have a pretty good sense of how this theory comes to be, where providing medium level data actually can harm individual and social performance. I'll then discuss our experiment where we test the predictions of this theory before discussing the results and then concluding and speaking a little bit more generally about kind of what we take away from this work. One motivation for our theoretical model is kind of what happened 2-3 years ago around COVID. So this chart is a snapshot of, in early 2020 about all the different efforts underway to discover a vaccine for COVID-19. As you can see, there's kind of the variation in phase 1, phase 2, phase 3, and phase 4. But what's really interesting for us is these different colors. And what these colors highlight is different vaccine platforms or different technologies that firms thought were the best way to find a vaccine for COVID. So the ones in blue are the traditional kind of deactivated whole virus technologies that firms are using. So for example, the kinds of vaccines for polio, we're going to use something similar to discover a vaccine for COVID. So there's a bunch of real investment dollars invested in that kind of technology. There's kind of what we haven't heard much about, which are modified DNA platforms and modifying DNA in order to discover a vaccine for COVID. And then there's kind of the thing that in the end is something that gets used a lot, which is mRNA platforms. But here you can see the kind of variation and uncertainty that firms have in terms of which of these different technologies is actually going to lead us to the promised land. And so what's common about this problem is that there's multiple firms engaged in costly high-stakes exploration under uncertainty. They don't know which of these technologies they should bet on. Second, it really matters both for the firm and for society that they kind of find this optimal technology, right? There's lots of high private returns as well as high social returns. And finally, there's learning across time and between firms. So if another firm succeeds in mRNA technology, I can see that, and I can start to adopt or start investing in that technology, as well as failures in certain areas are also visible to other firms. So these features are going to be quite important to our model. And we're going to model that in terms of multiple firms exploring across different options where they can learn from each other and where in future periods they can readjust based on their successes and failures of themselves as well as others. So what happens when there's kind of no data in the set? So imagine there's 5 agents exploring amongst 5 different options. They don't know which is the high value option, which are the low value options, and which is like a medium value option that could have been, that looks great, but isn't actually the high value option. When no information is provided, one thing that you'll get relatively certainly is a lot of exploration. You'll get a lot of diversity in kind of where firms put their investment dollars. So 2 people might choose option 1, one agent might choose option 3, and then option 4 and option 5. So 4 out of the 5 options might get explored. And even though most of these agents will fail and discover that actually the option that they choose is a dead end, the likelihood that someone discovers the high value option is going to be quite high. So in this case, an agent ends up discovering that option 2 is where the high value option is hidden. Now, imagine that I've shown some data. So in one case, I've shown data, I told firms that this is a low value option, right? So even before you start exploring, some uncertainty has been reduced. Or I told firms that option 4 is a high value option. The implications of this for search are pretty straightforward. When a low value option is eliminated, basically my decision problem is the same as before with one less option. That's going to make my search more efficient. And when I tell firms about the optimal option or the high value option, again, it's a very trivial case in the sense that all of the firms don't need to search. They can directly go to the high value option. So that's going to give us this mechanism that has been highlighted in past work, that data on low and high value options increases private performance and the likelihood of discovering optimal relations. Now, what's really interesting is what happens when I tell firms that option 2 might be medium value. So firms know that this isn't the high value option, but they also know that this isn't the low value option. So it turns out that by setting the value of M really carefully, I can shape this exploration process. In particular, if I set M to be high enough, I can set it so that M, the sure option of M, is higher than this value, because I'm going to quite likely fail in the first period. I'd rather bank a high amount in both periods rather than engage in any kind of failure in the first round. Right? So I can set M to be high enough so that it's attractive for firms to kind of behave in that way. But I can also set M to be low enough so that payoff is higher than this condition that we derived before when kind of no data is provided. So just to clarify the mechanics of kind of what goes on when we set M between these two thresholds. What we see is it's rational for agents to satisfy around this option M, reducing learning. So in the end, what happens, it's kind of a public goods problem where agents want to bank the M problem, the M option, and want others to explore. But all agents kind of behave in the same way. And so we get too little exploration under the M option. And so you can see how this A for sure reduces the likelihood that the global optimum is discovered. But also because we set the value of M carefully, this is actually going to be detrimental for a firm's own private performance. So that gives us this key prediction that data on the medium option decreases private performance and the likelihood of discovering the optimal option. Note some of the, so here's an example, right, which really clarifies this. So imagine that I have 5 agents and 5 projects. Everything I presented so far was kind of more general than that, but we'll kind of take these set of parameters to the experiment. So it's helpful to kind of think about that. In this setting, this is kind of the threshold for M. If M is below 1/3 L and 2/3 H, but above 0.6 L and 0.4 H, and there's a bunch of values of M in that zone, then we kind of get these options. So for example, M of 5 when L is 1 and 10 meets these 2 criteria. And if you work out what the payoffs are for agents under these 4 conditions, when I get the H, when it's told to me what the high value option is, I'm going to bank the H value so this is since this game is going to repeat over 2 time periods, I'm going to get a value of 20. When I tell firms what an L value option is, their payoff is basically playing the lottery amongst 4 options in the first round. And then because someone is going to discover H in the second round, banking 10 in the second round. So it's kind of 10 plus 4.25. If I don't give you any data, I'm still playing the lottery in the first half, but my payoff in the first round is 3.6 with the likelihood that someone discovers the optimal option in the second round. But what happens in the M option is everyone chooses the M period, and I'm going to get 5 plus 5, which is 10 in both periods. So you get kind of this prediction that my payoff from actually clarifying uncertainty, knowing where the M option is lower than when no data is provided at all, and obviously lower than the other 2 conditions when there's a bunch of data. So Melanie, question, how much does the value of the high option, et cetera, vary based on what other firms choose? What's the role for competition? So I'm going to state right off the bat that there's a few assumptions here, right? That we may or may not translate to different settings. So in one case, there is no rivalry. So if all the firms choose the same option, they all get the same payoff from choosing that option. So you can think about this as fitting much more a case where there's a knowledge spillover and firms can all benefit from that independently, as against a case where this market's hyper competitive and where it's kind of a zero-sum game. So this our parameters are not zero-sum, although they could be modified kind of in that direction. The other thing that I'll clarify is in terms of how information is revealed. So firms are going to completely see what other firms are doing at the end of each period. So that's also going to be important. Okay, so this is how we then frame this kind of theoretical setup and take it to the lab. We tell participants that their job is to find gems amongst a bunch of different mountains. So they have 5 mountains, and we bring in 5 agents at a time to play this game. They know ex ante that amongst these 5 mountains, there's 1 diamond, 1 ruby, and 3 topazes. And these are going to correspond to our high, medium, and low value options. So another simplification here is there's no true ambiguity, right? So firms know exactly the distribution of potential payoffs. And their goal is kind of clarifying uncertainty is kind of more important than knowing if I got a 5, whether or not that's really the global optimum. Firms can tell where a payoff lies in the distribution of potential payoffs. Then the game proceeds in 2 stages, as I've alluded to before. In the first stage, firms' agents are told these payoffs, and these payoffs change slightly throughout the game. So in this particular example, they're told that a topaz is worth $1, a ruby is worth $6, and a diamond is worth $10. Here, it's kind of player 1's turn to play, and she sees that another player has chosen mountain 1 already. So players pick sequentially, and she can choose between any of these 5 mountains. If she picks the same mountain as mountain 1, they would both get the same payoffs, or she could pick a different mountain. Now in this setting, since player 2 is kind of ambivalent between these different settings, on the margin, she's going to prefer to reveal more information rather than choose something that someone has already chosen before. And so player 2, once player 1 chooses mountain 1, player 2, for example, might end up choosing mountain 2, for example. And so at the end of the round, they don't see payoffs yet, but they see kind of what the other participants have chosen. And you can see that 1 person chose mountain 1, two people chose mountain 2, and 1 agent each chose mountain 3 and 4. Now at the end of this first stage, payoffs are revealed. So because 4 out of the 5 mountains were explored, all the players learned that mountain 1 had a topaz, mountain 4 had a topaz, mountain 3 had a ruby, and mountain 2 had the diamond. Okay, so this is the place where we all learn from each other's exploration activities. And in the second round, people can re-optimize. They can change their decision. So now it would be rational for agents to all choose mountain 2 because that's revealed to be the global optimum. And so people's payoffs at the end of both rounds are the sum of their payoffs in 2 rounds. So they don't get a free pass for making a mistake in the first round. So player 2, for example, would get $1 for choosing a topaz in the first round and $10 for choosing a diamond in the second round. So her eventual payoff would be $11. Now, in the experiment, we will shift how this baseline condition changes. We will tell them ex ante about the value of one of the mountains. So shining a light on the low value option would mean telling them, for example, that mountain 5 is a topaz, or telling them that mountain 2 is a ruby, or telling them that mountain 2 is a diamond, right? So the locations of these things move randomly across different mountains. And so we clarify uncertainty in different ways, depending on the experimental conditions. So in some conditions, as soon as they come in, they have 4 options which are uncertain and 1 option which has been clarified. And what we'll be interested in is how do the payoffs under these L, M, and H conditions change, both for the individual and for the group, as compared to the condition when there's no information at all. That's how we're going to model how data shapes exploration in this particular context. Just a little bit more on the logistics of how we actually collected our data. we had players come in and play 20 rounds of the game that you just saw. And so they played this kind of two-stage game 5 times with the same set of participants, and then played that round of 5 games 4 times. So in total, they engaged in this kind of activity over 20 times with 4 different sets of participants. Participants were completely unknown to each other, they were blind to each other, and there was no sense in which they could develop a reputation or develop any kind of networks amongst each other or learn from each other. And then they were told that payoffs will be based on a random round. Right? So even though they played 20 rounds, their incentive was to treat each round as being individual. So this really allows us to both get the most out of one participant. So make sure that we collect a bunch of data and have them participate in a bunch of different rounds, but treat essentially each round as quite independent. And I'll show you some data suggesting that this is a good approximation to kind of make it the same. I'll play this for like 30 seconds, but essentially a core part of our experiment was also some detailed instructions to participants on how the game would work. There were some complexities here, and a lot of that depended on creating a short 5 or 6 minute video that they all watched before they even got started with the game. Wondering if you can hear this.
Welcome. We are researchers at the University of Toronto and the University of California at Berkeley, and we are glad that you made the time to take part in our online decision-making experiment. We hope that the text instructions you just read were clear to you.
So participants read instructions and then they saw the video to really solidify their findings.
We'll go over some of the key points to help you understand this experiment better. In this experiment, you will be asked to make choices. Specifically, you will be presented with 5 mountains, and you will have to choose one of these mountains. Each mountain is linked to a gem. This could be either a diamond, a ruby, or a topaz. In total, there is 1 diamond, 1 ruby, and 3 topazes hidden inside the 5 mountains. Further, neither you nor your co-players have any idea about which gem is hidden behind which mountain. Note that there is a dollar value associated with each gem. For example, in this situation, each topaz is worth $1, the ruby is worth $5, and the diamond is worth $10. These values are examples and will change throughout the game. However, a diamond will always be worth more than a ruby, and a ruby will always be worth more than a topaz.
I'll stop it there, but it gives you a sense that there's some attention that was needed from participants, and we'll measure that. But overall, we did quite well on participants understanding the rules of the game and kind of what was going on. And that is kind of important too. Oops.
Well,
these videos. Sorry. Okay. In addition, there's a bunch of other logistics that I'll go over really quickly. In total, we had over 200 participants between the ages of 18 and 32. On average, the task itself, playing these 20 rounds, took them about 50 minutes, but there's a bunch of additional time to watch this video and understand the rules of the game. We elicited risk preferences using this halt and lorry task that I'll talk about in a second. Then on average, participants made about 20 USD or 26 Canadian dollars. That's because my co-author Johannes was at Toronto before, and all of this work was done at the Experimental Economics Laboratory there. This is kind of what the incentivized risk aversion task looks like. Basically, participants were asked to pick between things that were sure, like $4 for sure and $7.7 for sure. So it's pretty clear that you would kind of go with this option, but they were asked to pick amongst this entire menu for every choice. And by understanding kind of when they switch between something that's sure versus something that's risky, we can get a sense of kind of what their risk degree of risk aversion is likely to be. It's going to turn out that there isn't a ton of interesting variation here that's going to predict kind of what people do in the lab, but it acts as a useful robustness check. In addition, we pre-registered our hypothesis on OSF, as well as this experiment was IRB approved. Okay, so with that preview, let me talk about kind of the experimental results. The first thing one might want to ask is, Is it maybe also worth stopping here for a second? Any clarifications about the experiment? Kind of how it proceeded? Okay, great. In particular, one might be interested in asking what happens when what happens to individual returns across these two periods. So we saw in the example that that person made $1 and $10, so their payoff was $11. What's the average of that number across all players across the different conditions? And we had some predictions of that. The way we're going to measure outcomes in all of these charts that I'll show you is percentage of max. And this is partially because the value of the diamond changes across the different settings. So you can think about this as 2 times the value of the diamond. And so if I made 80% of the max, that means I made $16 out of the 20 potential dollars that I could have made. And so what you see is that in the no data condition, that value is about 75%. So people made about 75% of the max they could have made across both periods on average. This number goes up a little bit when no data is provided. So this is the value of taking out one option and the game kind of remains the same. And it goes up by a lot when I tell them exactly where the diamond is looking, right? And so this is also trivial in the sense that people just choose the diamond in both settings, and you can see it's almost close to 100%. Our first key result is that this payoff, individual payoffs go down when data is provided. So you can see that people actually make less money when they make exploration under uncertainty with value on the ruby rather than having no data at all. So each of these individual people would rather be in the no data condition rather than be in the condition where they're told where the ruby is. And we find that as kind of really the key validation of our theory. Here's another way to look at that. We see this is the distribution of raw and payoffs. You can see that apart from these few edge cases, almost everyone in the high value case banks in on the $20 that they could get. But it's really this medium value condition, which is constantly to the left of the other two conditions that you see here, right? So this isn't an artifact of some weird discrepancy in some cases. It's really a consistent result throughout our different experiments. And the same thing holds in a regression format. We see that on average, they make about $1.6 less against a baseline, I think, of about $10 or $11. So that points to about a 10% reduction in payoffs. Even more striking is if you care not about whether Pfizer or Moderna discovers the vaccine, but whether the vaccine is discovered at all, whether this group is able to discover the diamond. We call that the optimal option or the likelihood of discovering the breakthrough. We see that these numbers are quite high. So even in the no data condition, there's about a 90% chance of finding the breakthrough. And that goes up in the low and high data conditions, but it's dramatically lower in the medium data conditions. So there's about a 70% reduction in the likelihood of discovering the breakthrough option. And this we really see, and I'll show you more evidence of this kind of satisficing going on, where everyone kind of realizes that choosing the medium option is privately optimal for them, but socially that's going to be really suboptimal. And so here are the kind of different ways of doing that, both at the individual level as well as the group level. At the group level, this number goes up a little bit, but again, it's kind of the same thing that you saw before. Okay, so let's explore the underlying mechanisms here a little bit. And the best way to look at that is to look at the dynamics of what's going on between the different rounds. So what we can look at is how these payoffs change across the two stages, right? So in the first round, people in the low value condition, people in the no data condition are most likely to discover a low value mountain. And so their payoffs are not going to be that great. And what you see here on the y-axis and the x-axis are these different blocks. I mentioned before that there's the people play this game 20 times. So there's also a way to kind of see how these payoffs change as they become more and more experienced with the game. And the first thing you notice is payoffs are very similar across rounds. So this points to the fact that these rounds are kind of independent and we can kind of treat them as such. Then we see that people in the medium value condition actually make more money than those in the low and no data condition in that first stage of the game, right? So when there's a lot of uncertainty, I'd rather be told where the medium value is. That's going to be really valuable for me. However, this flips in the second round. In the second stage, what you see is people learn. Somebody else discovers the diamond and everyone else can readjust, while those in the medium data condition are kind of stuck in this local optimum. And so this really, I think, highlights the underlying mechanics of what's going on when we shine the light. So just kind of go back to the streetlight example. Here, what the streetlight is doing is it's crowding out private information generation, right? So it's providing uncertainty, but because it's herding other participants into where the light is, that's going to reduce the light that they would have generated from their own investment activities. So we think that there's interesting complementarities between public data and kind of these public signals versus private signals that firms can generate. Another way to look at this is to count exploration after period 1. So in the example that I showed you, after the first round, 4 of the 5 mountains were explored. So you can look at the correlation between how many mountains were explored in the first round and the likelihood that a diamond was found. And again, you kind of see this dynamic at play. So when no data is provided, in a large number of cases, about 50% of the cases, 4 of the 5 mountains are explored. And only in a few number of cases, the number is 2 or 3. And on top here is the likelihood that a breakthrough will be discovered. And you can see as the number of mountains explored increases, that likelihood goes up as well. When data on the L condition is provided, there's kind of 1 less mountain. But again, you can see in about half of the cases, 4 of the 4 mountains are explored. And in the other half of the cases, 3 of the 4 mountains are explored. So there's a large amount of exploration going on that, again, makes it really likely that these people discover the diamond in the second round. Same thing in H condition, there's obviously no exploration because everyone kind of knows where the H mountain is. What we see in the M condition is really quite different. There's a lot of zeros and ones in terms of how many mountains are explored. So you can kind of see that here side by side. So when I see this no data condition here, there's a lot of exploration after round 1. But when medium data is provided, there's 0, 1, kind of 1 is the medium number of mountains explored. So somebody explores 1 mountain apart from the medium mountain, but that's all that is explored. And so then the likelihood that we discover the diamond is only 28%. But even here, look, even when we get the 1% deviating from what they should be doing, this likelihood of diamond goes up from about 7% to about 30%. And the more exploration you get in these cases, the likelihood of discovering social optimums are quite high. So disobeying the streetlight in some ways can be really socially beneficial for everyone. Here's a visual of kind of what we just saw. And as I highlighted, this result is really robust across stocks. There's a bunch of different robustness tests that we do that I won't talk about now, but are documented in the paper, including bringing those measures of risk aversion and looking at kind of who deviates, etc. So let me conclude in kind of the 2 minutes that I have. So what are we trying to say in this paper? So our goal here really is to find a fine point or boundary conditions under which data provision might reduce rather than increase private and social returns in exploratory research. Our key contribution is this theoretical model that is inspired by the streetlight effect, but also which we think is quite original, that looks at how strategic multi-arm bandit models could be fitted to kind of the setting with group-based exploration over 2 time periods. And we provided experimental evidence, the goal of which we really see is to make sure that the kinds of deviations that we see human agents make are not big enough to overturn the results of our purely rational game theoretic model. And we find that to be the case. The experimental evidence is largely in line with the theoretical evidence. And the key result is that shining a light on these medium level opportunities can be worse than providing no data at all. And the key mechanism seems to be, that medium data can reduce exploration and learning, which can then reduce these kinds of long-term outcomes. So public data can rule out learning from privately generated data across these different agents. There's a bunch of extensions we document in the paper. In particular, you might not like this assumption we have about sequential moves, where one agent moves and then I can see their move and then go to the next stage. And turns out that's relatively simple to relax. And we show that the underlying theory holds with sequential moves. Another thing you might not like is that our data are kind of perfect. So they tell us precisely where the diamond is or precisely where the medium option is. But again, this turns out to not be critical to the underlying setup. I can tell you that So like in the examples pointed out before, I can tell you that this startup is more promising than the other startup, but I can't guarantee to you that this is the diamond. And that kind of data, or if there are costs to acquiring such data, we can kind of incorporate that in our model. Finally, from a public policy perspective, no one might know where the diamond is, right? So in our case, we as the experimenter knew precisely where to shine the light. But even here, if we randomly shone the light on one project, we would get this kind of variation. And so random data provision also doesn't seem to really affect the outcomes. One of the things that is a little bit out of the model and that we need to work on a little bit more is potentially the question that Melanie asked about rivalry. And we can accommodate small deviations to rivalry where maybe the second person gets 80 or 90% of the value of the first person. So order effects might matter, but those are things to think about a little bit more detail. So if I were to leave you with one last thought is we're in a world, if you're no matter where in which field you're in economics or finance or management, where the data revolution is kind of changing high stakes decision making and scientific exploration and investment and so on and so forth. And we often hear this rhetoric of kind of data being the new oil. So next time you kind of hear that adage, which has become trite to an extent, you should nod in agreement, but also question and ask what kind of data or what kinds of projects is this data illuminating? If it is really helping rule out crappy options or rule in really high value ones, then it is really valuable. But if it is indeed highlighting options, clarifying uncertainty about options that aren't those global optimal, data can act more like a siren, attracting explorers away from the promised land. And that could be really, really interesting. So thank you so much for your attention. I'm really looking forward to our discussion and for any other questions that you might have.
All righty. Thank you so much. That was great. Ryan, if you want to take it away, and then we'll have some time works for more questions later too.
Okay, how's that? Can you see my screen there?
Looks great.
Great. So really happy to have the chance to discuss this paper. And I think it's really interesting and very clear. If you read the paper, it's sort of, you can read it quickly because all the information is well organized and it's really well structured. So I'm going to focus my comments on some bigger picture, connecting this to kind of bigger picture policy and questions and economics of innovation generally, rather than going into some more of the details of the experiment itself, which again, I think was done very well. I'm coming at this from a very science-oriented perspective because that's what my research is about. I'll start with this comment that was in Nature magazine in 2011 by Edwards et al. They point out there's what they see to be a serious lack of exploration of unstudied proteins. There was this hope that during the Human Genome Project came was released in the early 2000s, that there would be all these new proteins that we could study. And there would be sort of like a minefield of, the opposite of a minefield, lots of opportunities to study new proteins. But they find that 75% of protein research still focuses on the 10% of proteins that were known before the genome was mapped. And so if you think of the light as being those sort of kind of very few proteins that we were thinking about before the Human Genome Project, maybe it's surprising that we haven't sort of branched out even with this kind of new map of potential projects. They say that much of the work that has emerged from exploring the human genome over the past 10 years lies fallow. They have this plot that I won't spend much time on, but this is sort of human protein kinases, one particular type of protein. If you look at the blue distribution of all of the citations to a very few proteins pre-2002, and then very little on sort of this long tail of proteins that were essentially understudied. If you look at 2009, now, a decade after the Human Genome Project, much of the distribution besides a few outliers is still focused on those ones that we knew about. And so they take this as evidence of under-exploration. So yeah, this is a topic that people are discussing sort of actively in science. And the problem of search in science and other areas, that we care about, scientists can either try to broaden or deepen our existing knowledge about the world, or sometimes we use like this exploit versus explore dichotomy. And, there's benefits to both. On one hand, it is useful to sort of deepen our understanding of things that are known, like digging under this, looking under the street lamp is, I think, seen as being a pretty productive task because there's just sort of more knowledge that can be gleaned out of existing topics. Exploring seems to be the hard part of it, going outside of the streetlight into new areas. And they make the great point, and my second bullet point here is that, depending on the result of a search, other scientists can use that information to either steer toward or away from that project. So I do think that there's a lot of potential for free riding here. These information spillovers can cause underinvestment in exploration because you're never going to be able to reap all of the benefits of your exploration, regardless of what you find. Other people are going to sort of also come in and sort of take some of the social benefits as, in kind of ways that will, lead to free riding. So I think it's a really useful question and relevant. I won't spend much time summarizing what they've done. Abhishek has done a great job of that. I think the model and the lab experiment match very well, and sort of it's almost like you read the experimental results and you say, of course it must be that, because that's, the model very clearly outlines where the free riding will happen and so forth. And so the key, again, finding is that the medium value areas lead to the least exploration when that spotlight is shown. This is the, the medium value project being revealed, this Ruby, and as we saw, you get a big underinvestment in exploration when that Ruby is revealed. Okay, so I'm not, again, I'll leave the specifics of the project for now and talk a few kind of broad points that I thought were useful and maybe helpful to thinking about future research in this area. First, let me say, let's try to map the experiment in the lab to what we see in the real world. I mean, lab experiments are obviously very controlled. And so there's a question of how can we sort of take those results and maybe study them in the real world. So first of all, where are the streetlights in science? I think this is one thing that maybe could use a little more clarification in the paper or just discussion more in the future is like, how much of a streetlight or what is a streetlight in the real world? I mean, on one hand, existing knowledge, like everything you can find on Google Scholar is sort of our streetlight, and that's what people have looked at. But of course, where did that knowledge come from? It sort of endogenously evolved over the history till now we have kind of this set of things that are known. And that feels a little different than, the spotlight effect in the experiment where we sort of get this random endowment of kind of a streetlight, some new knowledge, some new data. So where might that come from? I mean, in part, it's random chance. We think that probably lots of intellectual pursuit and discovery comes through randomness. I thought the COVID vaccine example was actually a good example of this, which is that, why did the mRNA prove to be the most valuable? Maybe it really is the best way to, the best technology to fight, COVID virus. On the other hand, maybe it's just that they got their papers out a little bit earlier. They registered their clinical trials a little bit earlier than like the DNA teams. And so maybe now we've heard it on mRNA, in part just because of the randomness of how that kind of race played out. I'm going to talk about races, not surprisingly, in just a minute. And so I think that happens in science all of the time. I don't know if there's a great policy sort of approach to that because that's just kind of the way knowledge is discovered. I think a really interesting one is like new tools. A lot of what the Edwards people talk about in this paper is that the proteins that we do tackle, that we see new people tackling, is in part because some new technology came out. We have a new tool to discover, certain types of research, and maybe you get some people focusing on that. But of course, the tool itself is potentially orthogonal to what the optimal direction is. So it introduces low-cost directions of research, but not necessarily sort of leading us to the global maximum best approach to solving some problem. And so, I think those are interesting to think through and maybe could be discussed a little more in the paper. Okay, so another thing I'll say is that, when we get stuck at one of these local maxima, what could cause us to break out of that? Why do scientists explore? I mean, we do see that we get breakthroughs in all sorts of areas. We're obviously not fully stuck at these maximum forever. And so what might cause that exploration? So this is a plug for some of the research I've done with Carolyn Stein, which is, the role of priority. And it sort of directly links to their model and experimental design, which is that and as Abhishek alluded to, the non-rivalry of rewards plays a pretty, important role in these dynamics, in that, once I've seen someone else discover something, I'm much more likely to herd there if I can also, mine out as many diamonds as they do. In some ways, that is how kind of science and new knowledge works, in that like ideas are cumulative. There in many ways, there's like plentiful opportunities to discover new things once a breakthrough has happened. But on the other hand, we sort of, through a system of priority rewards, have introduced some amount of rivalry. Okay, and this might be sort of socially contrived, but if you think about sort of priority races over history, we give a lot of credit, reputation, and even sort of monetary rewards to people who discover things first. Nobel Prize, you can make $1 million or, and get a lot of TV interviews if you discover something new. That's a low probability event, but it is out there. There are incentives, there are prizes, and even just sort of informal recognition that you can get through exploring and making a breakthrough. In our research, we find that even in, sort of one-on-one priority races, the team that wins gets maybe 20% more citation than the team that comes in second. So the question is that sort of contrived rivalry enough to drive exploration? You could think of an extension in this experiment, introduce something like a diamond finder reward or something. The first player to discover the diamond gets some sort of very large purse, and that would incentivize exploration, even in a case where the ruby is revealed. So I guess, broadly, then the question is like, do we have enough of those incentives to keep us out of these sort of middling equilibria? How large does the reward need to be to incentivize the sort of socially optimal exploration? And that's hard to figure out. I mean, people could over-explore too. Again, there's benefits from exploitation. So if you have these just huge rewards for exploration, rather than sticking with, kind of things that are going to be sort of socially valuable, everyone sort of scattering around in the dark, there's some balance there that's probably useful. I thought one thing that's interesting that came out of the paper is kind of this question of information disclosure. I think an unusual result of the paper here is that information sometimes is bad. A lot of settings in economics, we think information is usually pretty good, although that's not always the case. So this is kind of an interesting setting. So the paper suggests something like delayed disclosure of new results could be optimal. Are we sort of jumping onto sort of preliminary results too soon? Would we rather have scientists spend longer developing them, searching around more before they give their final answer in a paper? And we discussed that too in our work with where priority can sort of cause quality deficiencies in people's research if they're racing to establish priority. This does though push against the more common critique that science should be more open. I think we usually don't think about transparency as a bad thing, but maybe that's true. If there's too much herding, maybe we'd prefer a little bit more, not a little bit more delay for disclosure, or on the other hand, maybe just better communication about confidence bands. It probably is that we should be giving our results with a lot of sort of a lot of caveats to say, that this is the confidence we have over a result. Let's not rush into it until we kind of know that it's the right answer. And the last big thing I'll mention here is the promise of coordinated search. This is something that I'm personally pretty fascinated in that we often think of science in other areas, and especially like firm-driven R&D, as being very sort of motivated by private incentives. Investigator-driven science is all about sort of going out as your own lab and trying to make breakthroughs. There are alternatives, though. You can have very coordinated exploration in science. Some of the ones that come to mind are, again, the Human Genome Project, the Protein Science Initiative, the Sloan Digital Sky Survey. These are all examples where, rather than having investigators choose their own projects, we're just going to sort of have a list of projects that we want to go through, and we're going to assign people, to try them, and then we're going to communicate what we found. And we're going to be very careful to be disciplined about that to make sure that we've searched the whole space. So the benefits, of course, is that we avoid the duplication of effort and file drawer problems, but we can avoid the herding on rubies. That's kind of the goal here, is do a full comprehensive search. Of course, the challenge is that you need some sort of map of projects. So with like the human genome, there's sort of a set number of genes that we need to look at. But with something like economics, for example, how can you do a coordinated search of all labor economics topics? It's sort of impossible. It's undefined. So that becomes a much harder setting. And then also, you need persistent resources to sustain lots of failures. This was actually a problem with the Protein Science Initiative that was trying to map out the structures of all the proteins in the known proteome, is that everyone complained, all of the other R01 people complained that millions of dollars were going to projects that they thought were low value. It's like, we don't know anything about these proteins. Why are we spending all this time studying them? But the whole point was we're trying to get the whole map. We're trying to do consistent exploration, and it was very hard politically and sort of socially to keep that effort going. People didn't like it. So that's a potential challenge. Of course, there's also costs of communication, agency problems. People might slack off if they're part of these efforts. So those are kind of the challenges for our time, to think through whether moving in those direction for those types of institutions would be valuable. So just to close, thinking about future research here, again, I really like this paper. I think it's a great foundation to build on in terms of empirical papers or natural experiments in real world, settings of science and R&D. There's lots of great administrative data in science, clinical trials, other settings that we could dig into. I think more theory work here is great as well, understanding kind of the incentives in investigator-driven and coordinated search settings, and then also policy work. Again, these are day-to-day discussions that the NIH and other funding agencies have about, how are we getting enough exploration? Are people doing kind of the same old stuff, or are we pushing people into the frontier? And it's very hard to figure that out. So I think this is really active and important area. So I'll close there. Thanks a lot for the time. I enjoyed the paper and hope my comments were useful.